Hello and welcome to the Unit 6 Section 1 video on the Pythagorean Theorem. So the Pythagorean Theorem may very well be one of the most famous theorems that is out there. A lot of people know of at least the name of the Pythagorean Theorem, and it all has to deal with right triangles. The concepts behind the Pythagorean Theorem have been studied and used for thousands of years by the Babylonians, Egyptians, and Chinese. A Chinese manuscript shown from around 1000 BC actually illustrates this theorem. This is well before Pythagoras was ever around. So just because it's named after Pythagoras doesn't mean that he's the one who initially discovered it or was the first one to ever use it, because there is evidence that this was around. This is a figure here of a Chinese manuscript showing it with the modern translation on the right. Now, despite the evidence of it existing well before Pythagoras, the theorem is named for Pythagoras, who was a Greek mathematician from the 6th century, who is said to have been the first to write a proof of the theorem. Again, this could be debated a little bit, because this Chinese manuscript could very well demonstrate a proof of the Pythagorean theorem. But nonetheless, it is called the Pythagorean theorem. And it states that the sum of the squares of the measures of the legs equals the square of the measure of the hypotenuse. So, if C is the measure of the hypotenuse and A and B are the measures of the legs, then we can say A squared plus B squared equals C squared. And that is the famous line of math that everyone knows of, or at least has heard of, is A squared plus B squared equals C squared. A and B are the legs, C is the hypotenuse, and the hypotenuse again is the side that is opposite of your 90-degree angle. Now, many proofs of the Pythagorean theorem exist today. In fact, the U.S. President James Garfield, who took office in 1881 as our president, who was assassinated 6 months later, or was shot 3 months later, and then eventually died from his wounds 3 months after that, he wrote his own proof of the theorem in 1876. Now, the proof below, or the proof you see here, uses area and algebra, and you're going to notice similarities between the figures used here and those used by the ancient Chinese at the top of the page. So, first thing we're going to do to prove that A squared plus B squared equals C squared is we're going to take our triangle with legs A and B and our hypotenuse C, and we're going to arrange 4 copies of the triangle as shown here. Okay? Now, when we arrange those 4 triangles, we end up creating a square in the middle with side length of C. So, what do we end up with? Well, we're going to find what the area of this entire thing is. And to find the area of the entire thing, it is going to be, and I'll type this just for speed here, we are going to find that the area of the outer square is going to be equal to the area of the 4 right triangles plus the area of the inner square. Okay? So, what is the area of the outer square? Well, we know that the area of a square is side times the length of the length times the width, or the side squared, because the length and the width are the same thing. So we've got A plus B times A plus B, which is A plus B squared. The area of the 4 right triangles, well, the area of a triangle is 1/2 of the area of A times B, because if we did A times B, that would give us a full rectangle, but we have only half of that area, so it's 1/2 A times B, and you have 4 of them, so you've got 4 triangles times the area of each one, 1/2 AB, plus our inner square, which is C times C, or C squared. So, go back to your algebra skills. We are going to expand this binomial When you do that, you're going to get a squared plus 2ab plus b squared equals 4 times 1/2 is 2, so you have 2ab plus c squared. And you can subtract 2ab from each side, and we're left with a squared plus b squared equals c squared. So that is our first proof of the Pythagorean theorem. But there are many ways that we can prove the Pythagorean theorem. And so we're going to take another way of looking at this, and we're going to do it by using similar triangles. Now, part of this proof is going to involve some topics that we're going to be hitting later on in this unit. For now, take my word for it that when we take a line perpendicular to the hypotenuse that connects to the vertex where the 90-degree angle sits, then we create two similar triangles. And similarity is something that we just finished talking about in the last unit. So if we know that this medium-sized triangle and this little triangle on the inside of our big triangle, if we know they're all similar, then we can figure out some relationships. So we can say that our hypotenuse of our big triangle, C, we can set that to the hypotenuse of our medium-sized triangle, which is A. Then we can compare A, which is the leg of our big triangle, to the leg, the longer leg of our medium-sized triangle, which is X. So we end up getting A squared when we cross multiply. A squared equals CX. We can do the same with our small triangle. Compare our hypotenuse of the big one to the hypotenuse of our small one, which is B. Then take our leg, B, of our big triangle and compare it to the shorter leg of our small triangle, which is Y. Cross multiply and you get B squared equals CY. Now, let's add these equations together. So, A squared plus B squared is going to equal CX plus CY. Well, let's factor out a C. And when we do, we get C times X plus Y. But what is X plus Y? Well, X plus Y, if you use segment addition, is just C. So therefore, A squared plus B squared equals C squared. Now I'm going to encourage you, keep this in mind, you might want to make a note of it, but after we finish section 6.3, come back and look at this proof again, because you'll have a little bit more context to understand this proof. But I wanted to go ahead and show you this proof because we just finished using similar triangles. What we're using here is similar right triangles, and that's what section 3 of this unit is about. So again, I encourage you, come back to this proof after we do section 3 of this unit. So that gives us a couple of proofs, and there are many other proofs of this theorem, but that's just a couple of them. Now the Pythagorean theorem gives you a way to find the unknown side lengths when you know a triangle is a right triangle. So this is the practical application of this theorem. So let's do a couple of examples. So for example 3, we want to find the value of x. Well, we know, and we're going to use simplest radical form here, so we're not going to round using decimals on our calculator. You're going to have to simplify the radical when we do this. So we know a squared plus b squared equals c squared. That's our starting point. A, we can make 6, and b, we can make 4. It doesn't really matter which order you do this in because we're adding. So 6 squared is 36. 4 squared is 16. So 36 plus 16 gives us 52. So now we're going to take the square root of both sides. So the square root of 52, and this is where we're going to simplify our radical. Here's a little refresher on how to do that. You're going to see if a perfect square can divide into the number underneath your radical. So Our perfect squares are 1 squared, 2 squared, 3 squared, 4 squared, and so on. So those values are 1, 4, 9, 16, 25, 36, and so on. 49, 64, 81, 100, and it continues on from there. So you're going to see if any of those numbers divide evenly into the number underneath your radical. So for this one, and in this case, actually, let me go and correct this. All of these c squares, we're going to put in our value x, because that's what we're calling c here. So this should be x squared, x squared, x squared. So let's simplify this radical, and that should just be x, because we've taken the square root at this point. So x is going to be, well, 4 will go evenly in the 52. So we can divide this up into 4 times 13. And we can remove the 4 out, because the square root of 4 is 2. So we're left with 2 square root of 13. So that is the length of the hypotenuse, 2 square root of 13. And that is an exact answer, since we did not round a decimal. All right, for example 4, we're going to find the value of x. And we're going to, again, give our answer in simplest radical form. So we start with a squared plus b squared equals c squared. Our a is going to be 5. We can start with that, 5 squared. Our b, let's use our other leg, x minus 1 squared. And our c is x, so x squared there. All right, 5 squared is 25. And we're going to square this binomial. So you get x squared minus 2x plus 1 equals x squared. You can subtract a x squared from each side. So that leaves us with negative 2x plus 25 equals x, or actually equals 0. And it's 26 because we added the 1. So negative 2x plus 26 equals 0. We can move the 26 over to the other side. You could move the 2x if you wanted to. And divide each side by negative 2. And we get x is 13. So now that we have talked about the Pythagorean theorem, let's talk about identifying Pythagorean triples. So a set of 3 non-zero whole numbers, a, b, and c, such that a squared plus b squared equals c squared, is called a Pythagorean triple. In other words, all 3 side lengths of your right triangle are whole numbers. Your 2 legs and your hypotenuse are all going to be whole numbers. Now, like the theorem of the same name, there is evidence of the awareness of Pythagorean triples long before Pythagoras. The oldest known record of the Pythagorean triples comes from Plimpton 322, which is a Babylonian clay tablet from around 1800 BC. It was discovered by James Banks shortly after 1900 and sold to George Arthur Plimpton in 1922. It's now held at Columbia University as item 322 of the G.A. Plimpton collection. That is where it gets its name, Plimpton 322. So in this clay tablet, you can see all these markings. There is a way to read these markings, but all you need to know is that Pythagorean triples are listed in this clay tablet. So that is evidence of at least the acknowledgement that these sorts of relationships existed before Pythagoras, well before Pythagoras. At this point, we're talking about 2,500 years, 3,500 years before Pythagoras. So it's quite a while before Pythagoras was around. Here's a listing of some of the Pythagorean triples. In each case, the largest number is that of the hypotenuse, and the 2 smaller numbers are your 2 legs. So you've got a 3, 4, 5. That is one of the more famous Pythagorean triples. That's the simplest Pythagorean triple that you can have. You also have 5, 12, 13. The last example we just did, if you find the length of the other leg, you'll find it's 12. That was a Pythagorean triple right triangle. That was a 5, 12, 13. You also have 8, 15, 17, 7, 24, 25, And there are many, many, many more of these. But that's just 4 of them. So we are going to use that. We are going to find the missing side length and tell if the side lengths form a Pythagorean triple. So we'll pull out the Pythagorean theorem again. A squared plus b squared equals c squared. So a squared is 12. A is 12. B is what we don't know. And c is our hypotenuse, which is 15. So we have 144 plus b squared equals 225. Subtract 144 from 225 and you get b squared equals 81. And yes, we can take the square root of 81 and we get 9. Just as a side note, you'll notice that we're not using the negative version of the square root. We're only going with the positive version, and that's because we're dealing with lengths. You can't have negative length, so therefore negative 9 gets thrown out and we're just left with 9. Since the side lengths are non-zero whole numbers, that satisfies the equation a squared plus b squared equals c squared. They form a Pythagorean triple. So here we have a 9, 12, 15 Pythagorean triple. Okay? So now let's take a look at example 6 and do the same thing. A squared plus b squared equals c squared. Here we're given the two legs, 9 and 15. So we're going to see if the hypotenuse comes out to a whole number. So this is 81 plus 225. 81 plus 225 gives us 306. And the square root of 306 does not come out even. And just for the practice, we can divide 9 into 306 evenly. So that gives us 3 square root of 34. So since the side lengths do not form a Pythagorean triple, because 3 square root of 34 is not a whole number. To wrap up this section, we're going to talk about Pythagorean inequalities. So the converse of the Pythagorean theorem gives us a way to tell if a triangle is a right triangle when you know the side lengths. You can also use the side lengths to classify a triangle as acute or obtuse. So if we put an inequality in, or we see what their relationship is and use an inequality to describe the relationship between c squared and the sum of the legs squared, we can determine if it is obtuse or acute. If c squared is greater than a squared plus b squared, it's obtuse. If it's less than a squared plus b squared, then the triangle is acute. So, for example 7, we're going to tell the measures can be the side lengths of a triangle first, and then, if so, we're going to classify the triangle as acute, obtuse, or right. So, remember, to find out if it is a triangle, we are first going to take our two smaller sides, and we are going to compare it to our largest side. So 8 plus 11 is 19, and 19 is greater than 13, so we do have a triangle. So now let's compare and see if we have what type of triangle we have. So we're going to see what c squared is compared to a squared plus b squared. So c squared is 13 squared. Then we have 8 squared plus 11 squared. So 169, this is 64, this is 121. 64 plus 121 is 185, so 169 is less than 185, and so therefore it is acute. For B, we're going to see if 7 plus 12 is greater than 16. 7 plus 12 is 19. 19 is greater than 16, so we have a triangle. So let's compare c squared to a squared plus b squared. So c here is 16, a is 7, and b we're going to make 12. 16 squared is 256. We have 49 plus 144. So 256 is going to be greater than 193. So we have an obtuse triangle. Now, if we got straight up equals, then it would be a right triangle. All right, final example, 5.8 plus 9.3. We're going to see if that's greater than 15.6. Well, this ends up being 15.1. So that is not greater than 15.6. So therefore, we don't have a triangle, and that's as far as we can go. All right, so that finishes off our section on the Pythagorean theorem, what we can do with it. Coming up in the next section, we're going to talk about special right triangles, and we'll talk about some of the shortcuts on how to find sides given these special right triangles.